Okay, so let's actually take a look at the effect of this by, I'm going to set a breakpoint here. I'm also going to set a breakpoint here. So does everybody know the effect of a breakpoint? So when we run to here, it stops before running this line. So not after running this line, before running this line. So we are going to be stopping right before it goes into the solving the error equation. We are also going to stop right after we solve the error equation. We interpolate the solution of the error equation from cost to fine grid, and before we add the solution of the error equation onto the current solution. And let's take a look at what it does. So this is calling recursively the multigrid, but for one cycle, exactly for one cycle, like what we did here. All right. Okay. So first, it stopped over here. See the green arrow? We stopped before we call it multigrid. And I like to bring your attention to the lower left box. These are the current variables that are being processed. We see that U is the current solution after the first pre-smoothing, and R is the computed residual. It's as big as U, but RC is now a reduced residual on the interpolated to the cost grid. If we do I am sure of what U is, you wouldn't see it, but like let's times 10 to make like it clear on that picture. Otherwise, only I can see it. You can see like you have only the very high frequency content of the solution. I mean, it looks like an airplane, but like only the contours. That is the very high frequency content of the solution. All right, remember we did the last lecture, we did the analytical solution minus this solution. It's like a blurred version of the airplane. Okay, so let's keep going. Let's push continue. And where do you think it'll stop next? Would it stop at line 18 next? Or 17? Huh? 12. Why? It is a recursion. It'll be calling multigrid, and within that multigrid, it'll stop right over here. So we are basically setting a breakpoint every time it goes down here, and we are also setting a multigrid breakpoint every time it goes up here. So next time it'll stop at the same line, but at a deeper function call. So let's see if that happens. Continue. Okay, it stopped exactly still at line 12. But if you look at the size of the variables, they are smaller. They are smaller. Now my solution U is the solution of the error equation after the pre-smoothing. So let's do I am sure of U times 10. Okay, no longer produces the error message. The image is too large, and we see it's like a thicker contour, right? It's the slightly lower frequency content of the solution, not the extreme high frequency, but like slightly lower. So let's continue further. Again, it stops at line 12, and U is even smaller. If you do I am sure it's a smaller image. If you magnify it, like the line is even thicker. And continue again. The U is now 129 by 129. It's a smaller image and looks like that. Now you can see the pixels. Maybe not on that, but I can see the pixels. And let's go further. Next time you for sure see the pixels. Right? Okay, now we can see like we get thicker and thicker contours. And let's keep going. May become a little bit boring. These are like tiny images, but this is the lower and lower frequency content solution. Let's keep going. And 9 by 9, what is that? Okay, it looks something like that. And keep going. I believe we are going to get a, yes, well, last time it was 17 by 17. This time it's a 9 by 9. Okay, it's just something like that. Are we still gonna go further? Oh yes, we get a 5 by 5. All right, so that's the causes grid solution. I don't believe we are going to go into any more. And now continue. We are at line 18. We have solved the error equation. So when we are at 3 by 3, we are just doing the pre-smoothing and post-smoothing. Okay, that's when we are at a 3 by 3 image. At a 3 by 3 image, only one pixel is the solution. Everything else is the boundary condition. So we are solving on the 3 by 3 image, we are solving a linear system of size what? What? 9 by 9? 1 by 1, because like the 8 pixels around it are boundary conditions. We are solving a linear system of 1 by 1. It's just an incredibly easy linear system to solve. Like every iteration of this, actually, like if you are actually writing a code on that 1 by 1 system, you shouldn't. I mean, it doesn't make any sense to like do iterative method. You just it's an algebraic equation to solve, right? I mean, in here, because I don't want to write too much code, I just do this. It's not harmful. Okay, so anyway, on the 3 by 3 image, I solved the system very accurately because I'm doing 10 iterations of an incredibly easy system to solve. So if I now u should actually be the same. So I haven't changed the u from here to here, but so u is the same. You're gonna see that u is the same. But if I also do I am sure of e, well, it's not much to see. So actually let's go to a closer grid. Let's go to a finer grid to see actually the effect. So okay, so we go on further. U becomes 9 by 9, and let's go to something about like 32 by 32 to see the effect. Okay, so let's start to see. So first of all, U is the same thing as what we saw before. It's exactly the same thing as we saw before because we haven't changed it. Now let's see what E is. E is this. It's an interpolation of a coarse grid solution. So it's like a smoothed version of the solution, right? Okay, now if I figure and plot this U plus E. Oops, not plot. I am sure. You compare this against this. You see the effect of the pre-smoothing we have done. The effect of the pre-smoothing, which in the beginning are just a few lines of contours, now provides the missing high-frequency content of the solution. So this is the error equation. This is the error equation plus the solution after the after the pre-smoothing. Right? Do we all understand what we are looking at here? Let me also plot the U itself. I am sure of U. You probably can't see much. Let me still do the times 10. Okay, so this is the U itself. It just provides the contours. This is the figure 2 is the E. Figure 1 is the E, is the solution of the error equation interpolated from the coarse grid. And figure 2 is U plus E. It's like the contours plus the blurred solution coming from the coarse grid. It's now a much better solution. Close all. Okay, let's keep going forward a little bit. Let's go to the 64 grid and 128 grid. And again, oh, no, I am sure. So this is the contour-like image we saw before. This is the error equation coming from the cost grid. Looks like blurred. U plus E now is a much clearer image compared to this of the solution, right? Okay, and we keep going to 257, going up this grid V cycle. Remember, we have a V shape. And now finally we get back. So remember, U is this very contour-like picture, and E is already a pretty good solution because it adds up like all the grid levels. And I don't know if we can see the effect, but like U plus E just makes the image now a little bit more crispy. Oh, maybe you can see that. Can you see the difference? Especially like look at the gap between the main wing and the flaps. Not very clear on that one. Okay, okay. So basically, that's how the multigrid cycle works. Now, if I continue, it'll return me a U. Any questions on how this works? Like when you're solving a more complex equation or on a more difficult grid, each component may be more complex. Like the well, you may also use a more advanced smoother, right? But it's still pre-smoothing, and interpolation from find to cost. Maybe you need a more complex interpolation scheme, but it's still interpolation from a find to cost, and then recursively call the cost grid solution to solve the error equation, and then interpolate the solution of the error equation from the find grid to the cost grid. From the cost grid to the find grid, and then do a post-smoothing. The steps are going to be exactly the same, and the effect you should see on the solution should be exactly the same. Yes? Yes. Good point. So what I mean by high frequency content is if you perform a Fourier transform, it like the high frequency component of the Fourier transform shows up. Intuitively, what that means is that a high frequency means on the grid, especially on the grid, means anything that cannot be accurately represented on the cost grid. So for example, if you have a solution that looks like this, can the solution be represented on a cost grid? Let me change a color. Let's say the cost grid is only this grid, and this grid. If you perform an interpolation of that solution onto the cost grid, you would get a solution like you would pick up this point, pick up this point, pick up this point. Instead of a function that looks like this, you get a function look like this. It's completely different. On the other hand, if you have a solution only with low frequency content, let's say you get a solution like that. Okay, then when you pick up the same solution at a cost grid, you get this, and this. It's still a good approximation of the original solution. So that's, especially in the multigrid context, that's the difference between a low frequency content and high frequency content. You can usually decompose the image into two parts. One part is the kind of modes that can be supported by a cost grid. I mean, there is this Shannon sampling theorem. I don't know if you are familiar with. It's kind of beyond this class, but the theorem basically says that if the frequency and content of a function is low enough, then on a certain grid you can reconstruct that function exactly. So that's, I mean, from a mathematical point, that's what it means by low frequency content.